Okay, the purpose of this screencast is to carry out a non-linear analysis in ANSYS, and the example we're going to use is the example covered in the lectures, which is a cantilever supported by a torsion spring. So here's the definition of the problem. We have a cantilever which is 1 meter long, and at the left hand end we're supporting it with this torsion spring which has got a stiffness of 10 Newton meters per radian, and at the right hand end we're applying a force which remains vertical at all times, and the size of that force is 30 newtons. Now, when we carried out the analysis by hand, we divided that 30 newton force into 6 equal increments of 5 newtons, and this was the result that we obtained. So what we're aiming to do in this screencast is to show how that same analysis can be carried out using ANSYS. Okay, so again this is going to be a static structural analysis, so if we drag that in and create this analysis, and we will call this a torsion cantilever. Okay, and we don't need to mess around with engineering data because the standard structural steel will be fine for this example. So the next thing we need to do is to open up the design modeler by double clicking on geometry. Okay, so here we are in design modeler. Let's just check the units. The units are in meters, which will work for this analysis. So we really need to check there. And the first thing we want to do is to define a cross section to use for our beam. So we've got a concept with a cross section, and it's going to be a rectangular cross section, and the cross section defaults to being 10 millimeters by 10 millimeters, which will be fine for our analysis. And the default section name must come up as rect1. Let's change that, let's rename that to square, so we have a square cross section. So that's our cross section defined. We now need to define where our beam is going to be, so we're going to do this on the XY plane. So go to the XY plane. If we want to look directly at that, then we can click on the Z direction there, so we're looking at the plane, and then go into sketching. Now, a way of setting up the grid in sketching so we can see what we're doing is to go to settings, and we can turn the grid on and check what the spacing is. Oh, the major spacing here is defaulted to 5 meters. Might be a bit long because we're only creating a beam 1 meter long, so let's change that to 1 meter. The minor steps per major step is 5, so that will work fine. Okay, so here's our grid now, and if we just zoom out a little bit, then that is going to be 1 meter. So we now need to draw a line in there which is 1 meter long. So that's our line created. Let's go back into modelling now, and this time we'll go to concept and we'll create a line from the sketch which we have just created. So we've got lines from sketches, and the base object is going to be the sketch. So if we apply that, then we have now got our line from the sketch. And we can now generate from that. Okay, so there's our line created. that's created a body called a line body. Let's rename that to something a bit more sensible as well. We'll call that beam. So that's our beam. Now you'll see down here that the cross section is highlighted because we've not selected anything, and if we click there we'll get a drop down which allows us to select that square cross section we defined earlier. And if we want to see that cross section, if we go to view and select cross section solids, then we will see the cross section. We'll have to zoom in a bit to be able to see it clearly because it's quite a small cross section, but we can now see that we've got that square cross section for this beam. And at this point it's sensible to save the project. Okay, so here is the model imported into ANSYS Mechanical, and the first thing we need to do is to make sure that we are using the correct units. So units, and we need to make sure that we are using meters. So set the units to meters, and we could also do is seeing the cross section rather than just a line. So if we go to view, and we can then select cross section, so we actually see the cross section of the solid. Also useful in the units to make sure that we are using radians. That will simplify the input and make sure that this example matches the hand calculation example. Right, so we've now got our beam imported into mechanical. We now need to create at one end of the beam this torsion spring, and we're going to do that by creating a connection. So on the model we need to insert a connection. So if we go to model, insert, and then connections there. So we're creating a connection, and if we right click on connections, and we are inserting a joint. So here is the joint details window, and there are a number of things that we need to complete here. The first thing we need to do is to change the connection type. At the moment it's set to body to body, so that's we'll be connecting this beam body to another body. We need to be connecting it to ground. The type of joint that we're going to be using is going to be a revolute joint, which is the same thing as a hinge, and we need to give that a torsional stiffness, and we want the torsional stiffness of 10 Newton meters per radian. We haven't yet defined exactly where this hinge is, so that's why the scope says no selection. So we want to be picking a point on the end here. Now in order to do that we need to make sure that our selection option up here is set to vertex / node, so that we can actually pick a point on the end. We can then pick a point on the end of the beam there, and we can apply that as our reference point for this connection. Okay, now that we have defined our hinge joint, we'll see that it is called revolute ground to beam, which isn't brilliantly informative, so let's rename that and call it hinge. Okay, so if we expand the tree underneath hinge, we see that we've got this reference coordinate system. Purpose of this is to define the axis of rotation of the hinge, and we need to make sure that's in the correct direction. So if we select the end of the beam where the hinge is, so that's that end there, and we can see the coordinates are appearing, and it's the z-axis which is going to form the principal axis of rotation. And if we look down here at the principal axis, the axis is actually the z. We need to make sure that we have selected the correct axis, and we are defining that using the global z axis. Right, so that's defined our hinge joint. If we then right click on mesh and select generate mesh, then we can use the default mesh. So we've got a number of beam elements created along the length of that beam. That should work fine. We now need to generate the load. So if we go back to static structural, and we can create a load, which is going to be a simple force, and we want to apply that force to the other end of the beam, so this end here. So that's where we're applying the force, and we are going to define the force not using a vector but using components in the global coordinate system, and we need to apply a force in the y direction, and the force we need to apply is 30 newtons to match the hand calculation. So there's our force of 30 newtons applied. We're now at the stage where we need to set up the non-linear solution. Make sure that we are controlling the analysis in the correct way. So if we click on analysis settings, then we'll see down here that an awful lot of this is controlled by the program. We want more control than that. The first thing we need to make sure we've got is that we are accounting for large deflections. By default we don't, so we need to turn large deflections on. Auto time stepping, let's turn that off so that we can control what's happening, and we are going to make sure that we carry out this analysis using 6 increments, or what ANSYS calls substeps. That will match the hand calculation again and forces ANSYS to use increments of 5 newtons. We'll see here that weak springs can be introduced, and that's to prevent rigid body motion. Weak springs may cause our analysis to deviate from the hand calculation. So let's take the weak springs off. So that should now have defined our analysis correctly. So we've got a total time step of 1 second. We are using 6 substeps, or 6 increments. We're accounting for large deflections, and we are preventing weak springs from being introduced. Right, under the results, the sort of results we want, so click on solution. We want total deformation. We want some beam results as well, so if I right click here, insert, and we go to the beam results, we want the bending moment in the beam. and we also want to know what's happening in the joint. So again, right click, insert, and this time we're going to probe what's happening in the joint. And under this joint probe window, we need to select the particular boundary condition where we want the result, which is the hinge, so the one that's actually available to us. And the type of result we want is not total force, we're interested in the total moment. Right, we should now be able to solve the analysis. So running that. Okay, so here are the results of the analysis, and first of all, looking at the total deformation, we can see that the beam has rotated by a large amount, but there is very little actual bending in the beam. Look from the side, and just close that down a little bit, and the beam is still almost straight, and it's rotated up through quite a significant angle. If you look at the bending moment that we've got in the beam, here's the bending moment, and the maximum bending moment is only 11.5 Newton meters, not 30 Newton meters, despite the fact that we applied 30 newtons to the end of a beam which was 1 meter long. And that, of course, is because the line of action now of the force is much less than a meter from the hinge point. And we can also see that this bending moment increases non-linearly down here in the little graph at the bottom. If we look at the joint probe, then again this shows us the reaction moment, and the reaction moment about the z-axis down at the bottom here is equal but opposite to the bending moment generated in the beam, so that goes up to a magnitude of 11.5 Newton meters again, and again we can see that it's non-linear. We go through the increments of load. If we select the solution information, then we get the text output from ANSYS initially, which isn't particularly useful, but if we go to the solver output option down here and we change that to force convergence, we can then see the way that the force has converged and reduced to a very small amount at the end of each increment. So these green dashed lines here represent the end of each increment, and we can see how the forces converge down. We can also get a good idea of how many iterations were required to get the required force convergence. So there's an increment in the middle here where it was actually quite difficult to get that convergence to occur. Okay, so that was a non-linear analysis of a cantilever supported by a torsion spring.